Our data records the responses of grade 11 entrants or grade 11 students as to their preferred as senior high school strand that they would like to enroll. We have here 1 until 200 students, and they were able to respond on their preferred senior high school strand. We have the TVL, we have the STEM, ABM, and UMS. Now, if you would like to determine whether this set of responses is similar to the expected result, like say for example, if DepEd claims that our grade 11 entrants show no preference with their senior high school strand selection, we can use here a certain test to verify whether this observed results is similar or not significantly different from our expected result. Here, we are going to use the chi-square test. More specifically, we are going to use here the chi-square goodness of a fit test. The chi-square goodness of fit test is a test that is used to compare observed and expected results. It is used to determine whether a distribution of cases, in this case, the distribution of responses of our grade 11 entrants in a single categorical variable senior high school strand follows a certain hypothesized distribution. In this case, the distribution hypothesized, for example, again, the claim of the DepEd that our grade 11 entrants doesn't have any preference. That would mean that the enrollment or the preferred senior high school strand enrollment of our grade 11 students rather are of equal distribution. Okay, so we are going to use here the chi-square goodness of fit test to that as to determine whether there's a difference between the observed result, the observed data with the expected equal distribution. To start with, we are going to look at the assumptions before we could really use the chi-square goodness of fit test. The assumptions before we could use the goodness of fit test, and we are going to determine it or examine it here. Number one, we should only have one categorical variable. In this case, we only have one categorical variable, the senior high school strand selection. It's called categorical variable because the responses are categorized in different independent forms like STEM, the ABM, UMS, and TVL. That's our first assumption, and since our data here meets that criteria, then of course our first assumption is correct, already achieved. The second assumption is that there should be independence of observations. That would mean that the response of student number 1 is independent to the response of student number 2. Their response is not necessarily affected or dependent on what is the response of the other respondent. Okay? And with that here, we are going to assume that the assumption has been met. The third one here is assumption number 3, that our observations or responses are mutually exclusive. That would mean there should only be one response per student. Our one student here, say for example, if we're going to interview one grade 11 entrant, he or she could only respond 1 out of the 4, STEM, ABM, UMS, or TVL. Any second response should not be recorded, or that student or the response of the student should not be included here. And since we already have recorded student number 1, STEM, and assigned their responses, then that would mean we have mutually exclusive observations. And the fourth assumption for a chi-square test is that in our list of expected frequencies later or expected results or outcomes, there should be at least 5 per each category. Obviously, we have here 200 students, and there are obviously more than 5 STEM responses, UMS, TVL, and ABM. So that is already met. And we could also verify it later as we have our statistics later. So all 4 assumptions for a chi-square goodness of fit test has already been achieved. Hence, we can use that. Before we can start with analysis, let's go back here for our variable view so that we could be guided. Our first column, student earlier, was just for our representation of the student. And our second column, senior high school strand, would be the preferred senior high school strand here. And So such that we can actually apply a certain analysis later, we are going to assume certain variables for our responses. So if we're going to click this one here, the response is already done. So 1 would be stem. You can input like this, 1 and then stem, but since it's already there, so you don't need to do that. Okay, you just simply click add, and since it's already there, so you just need to delete this area. But that's how we signify our or label our values, because we are going to use the values in determining the count later. Okay, because we were going to add the number of stem responses, etc., etc. And of course, both of our data, or more specifically our senior high school strand, is nominal data. This is a categorical data which is only applicable for chi-square test. Okay. Now, going back here, and before I would go back there, again, don't forget that we have these numbers. We already also have this trick in our SPSS. If you just want to see the numbers here, simply click this button. Okay, you will have 1, 2, 3, 1, 4, and of course, if we're going to click that again, it will return to the assigned values here. So 1 would be for STEM, 3 would be UMS, 4 would be TVL, and 2 for ABM. I'm going to do that like that. Okay. Nevertheless, that's just one trick that we can use here. So let's consider this hypothesis so that we could use this in our interpretation later. Our first hypothesis, the null hypothesis, is that the grade 11 entrants show no preference with their senior high school strand selection, as our null hypothesis is the hypothesis of no difference. Of course, if we cannot reject this, then it should stand that the preference of grade 11 students are of equal distribution amongst the 4 senior high school strand. Of course, our alternative hypothesis would be grade 11 entrants show preference with their senior high school strand selection. That is only true if we are to reject our null hypothesis. We could reject our null hypothesis if we could get a p-value of less than 0.05. That's the region of rejection with our 95% confidence interval, or 5% or 0.05 level of significance. And if this will happen, once we reject our null hypothesis, we can say that yes, there is preference amongst grade 11 entrance senior high school strand selection, which could our refute, or not necessarily refute, which would be against the claim of a depth that we are trying to look at of equal distribution earlier. Okay, so with this all in mind, we can now start with our analysis. We can start our analysis in this manner. We go to Analyze, you click that, you will have to proceed to the non-parametric tests here. Once you go to that, go to Legacy Dialogues, and once you hover to Legacy Dialogues, you will see your chi-square. Again, Analyze, we have here non-parametric tests, Legacy Dialogues, and chi-square. This is the process specifically for goodness of fit test. We also have another test for what they call this one, chi-square. We will be using different pattern to that, but this would be for our goodness of fit test. So let's click this chi-square, and you will see this dialog or dialog box. Now we can see here our 2 columns. You simply click the preferred senior high school strand, which corresponds to our second column, and click this button to be placed that in our test variable list. Okay. Before we click OK, I would like to bring your attention here. Take note that our first concern is to determine whether the senior high school strand selection of grade 11 entrants are of equal distribution, which was supposedly the claim that we are trying to determine here for our depth ed. So this is the default here, all categories equal. So that's automatically checked. Now, we will also have a separate video for this, a continuation for this same set of data, still under goodness of fit test, but that is with the change, the idea that there are now specific preferences. So we're going to use here the values that will be on a separate video. Don't worry of that with that. Just for the meantime, let's have this all categories equal. Okay, let us visit options. Okay, let's click descriptives, because descriptives will help us talk about the responses as well. So we're going to continue that, and then again, now with all categories equal, let's click OK, and you will have this result. Okay, so you have here 1, 2, 3 different tables. So let's talk about them one by one. The first table is just the descriptive statistics. We checked earlier using our options because we just would like to see if everything has been recorded. 200, everyone is recorded. You have here our mean is 2.3. Take note, this is the mean of the labels that we use: 1 for STEM, 2 for ABM, 3 for UMS, and 4 for TVL. So those numbers are just nominal in nature, so we don't need to really expound this here. But at the point, if we would like to talk about this one, so that is our descriptive statistics. Let's proceed here on our frequencies. Let's have our first table. This first table, in the first column here, these are the total frequency of the list earlier. If we're going to go back here, we have 200 students. Okay, if you're going to count them manually, okay, you will just return to this. So SPSS already give you the observed sample size per responses. So 65 answered STEM, 50 answered ABM, 45 for UMS, and 40 for TVL. Now, what is this second column? This is the expected N because we clicked earlier the all categories equal. So there are 4 categories and there are 200 students, so it will divide 200 in 4 equal parts. So that's 50, 50, 50, 50. Okay, this is what will happen because we just simply let all categories equal as it is. Okay, if we're going to do the second thing on the next video, this will be changed. The residuals are just the differences: 65 minus 50, like that, 50 minus 50 is 0, and then this one here. Now, this expected N will only be true if there's no significant difference. Even if we have clear differences of 65 to 50, 50 to 50, 45 to 50, even if we have these residuals, is the difference with are the combination of residuals significant? That's what we would like to determine and is answered already by this last table. Focus here on the first, that's our chi-square value. Okay, we can do it manually as well, but that's our chi-square value, and we're going to compare it on our region of rejection, which is placed on a chi-square distribution. But we already used SPSS here, so let's continue. The degrees of freedom is N minus 1. That's 4 categories minus 1 or 3, and this is our significance value, 0.072. This is greater than 0.05. What does this tell us? If our p-value is greater than 0.05, then we fail to reject our null hypothesis. That would mean that grade 11 students show no preference on their senior high school strand selection, even if we can see here that there are clear differences between the count, 65 to 50, 45 to 50, and 40 to 50. These differences doesn't amount to a significant difference because of this p-value. Hence, again, we fail to reject our null hypothesis. Now, this A here is just another indication that all of our expected value has less as greater than 5. As mentioned, that's a fourth assumption for chi-square test, and we can see here that each of our expected value is greater than 5. That's why it's 0% of cells has less than 5, and that's already okay, because if this is greater than 60%, then we're going to use another method, other test for that. So going back here in our data, we can see here that even if the responses of our 200 grade 11 entrants are very varied, and they amount to different counts for STEM, ABM, UMS, and TVL, those counts do not necessarily give us significant difference. That would mean, as mentioned, for this specific gathered data, we can now show that the claim of DepEd that grade 11 entrants show no preference for their senior high school strand selection is enough to say we have evidence enough to say that it's closely correct to that, and the grade 11 entrance has no preferences. Okay. Now, we will have a separate video, still continuation of this, but we are going to talk about what if there are certain differences now in expected value. But then again, that will be for the next video. So, see you on the next video.